What is the force between two small charged spheres having charges of 2 into 10 minus 7 coulomb and 3 into 10 minus 7 coulomb placed 30 centimeter apart in air? Let us assume air is homogeneous and isotropic and endless, and also assume permittivity of air is nearly equal to permittivity of vacuum. So the formula used 1 by 4 pi epsilon A actually, which is nearly equal to epsilon 0, Q1 Q2 mod by R square, Q1 given, Q2 given, R given, then we can put the value and we can find the answer. So 1 by 4 pi epsilon 0 value, Q1, Q2 both are positive. Since Q1, Q2 both are positive, so Q1 mod is itself, Q2 mod is also itself, and 30 centimeter converted to meter. So answer coming 6 into 10 minus 3 Newton. The electrostatic force on a small sphere of charge 0.4 microcoulomb due to another small sphere of charge minus 0.8 microcoulomb in air is 0.2 Newton. What is the distance between the two spheres? What is the force on the second sphere due to the first? The two spheres behave as point charges. Q1 given, Q2 given, force magnitude given, then the distance is asked, and the force on second sphere due to the first sphere is asked. The problem is based on Coulomb's law, Newton's third law. Formula used is F equal to 1 by 4 pi epsilon 0 Q1 Q2 mod by R square. F is the magnitude of force between the two charges. So R is coming, then putting 1 by 4 pi epsilon 0, Q1 mod is positive, Q2 mod is also positive, then F is given, then the R is becoming 12 into 10 minus 2 meter. Electrostatic force obeys Newton's third law. So force on Q1 by Q2, force on Q2 by Q1, they are equivalent, opposite. So the magnitude is same and direction is opposite. And since the two charges are unlike charges, so they attract each other. Check the ratio. This much is dimensionless. Determine the value of this ratio. What does the ratio signify? Electrostatic force between electron proton K E square by R square. Gravitational force between electron and proton is G MEMP by R square. So R square cancelling, the ratio of magnitude of electrostatic force to the magnitude of gravitational force between electron and proton is coming this much. It is since the ratio of two forces, it has no dimension, and the value is K value 9 into 10 to the power 9, E square, G value, ME, MP. So after putting, the result is 0.3 10 to the power 40. It is actually the ratio of electrostatic force magnitude to the gravitational force magnitude between electron and proton. Explain the meaning of statement electric charge of a body is quantized. Robert Millikan discovered that the charge of any body is of the form Q is equal to Ne. N is integer, E is the elementary charge or quantum of positive charge or charge of a proton, and E value is this much. Why can one ignore quantization of electric charge when dealing with macroscopic, that is, large scale charges? Quantization of charge says Q should be Ne. So N is Q by E. Q by E. Let us assume E is equal to 1.6 10 to the minus 19 coulomb. This 10 to minus 19, it is coming to the numerator. Multiply 10, divide 10, it is coming Q into 10 to the 20 by 16 coulomb. This is Q by coulomb into 10 to the 20 by 16. Q by coulomb 10 to the power 4 by 16 into 10 to the power 16. This 10 to the power 4 by 16, it is 625. This is an integer. 625 is integer. Q by C may not be integer. So in most cases, or there is a large probability of Q by C when multiplied with 10 to the power 16, also when multiplied with 625, the whole result is an integer. So that is why any macroscopic charge, if Q is, then there is a large probability of this becoming an integer. This may not be integer. When it is multiplied with this and this, there is a large probability it will become an integer. So any macroscopic charge, we blindly support its possibility, but if it is a microscopic charge, we will check whether the n is an integer or not. When a glass rod is rubbed with silk cloth, charges appear on both. A similar phenomenon is observed with many other pairs of bodies. Explain how this observation is consistent with law of conservation of charge. When glass rod is rubbed with silk, glass rod becomes positive. So glass rod loses electron. The same electron is gained by silk cloth. So silk cloth becomes negative. The glass rod and silk comprise an insulated system. So the algebraic sum of charges of the insulated system remains constant. Hence, the conservation of charge is applicable in this situation. Four charges, point charges given QA, QB, QD, QG, corners of a square ABCD of side 10 cm. What is the force on the charge 1 microcoulomb placed at the center of the square? The problem is based on electric field due to point charge, superposition principle of electric field, relation between electric field and force. So the corresponding formula E vector. Superposition principle says E vector equal to E1 vector plus E2 vector plus E3 vector, and the relation between electric force and the electric field. The charges QA, QB, QD, QG. Let us find the electric field at O due to the individual charges. EA is electric field at O due to QA 1 by 4 pi epsilon 0 QA by R square N1 cap. N1 cap is unit vector directed along AO vector. EB vector, electric field R2 due to QB, 1 by 4 pi epsilon 0 QB by R square. N2 cap. N2 cap is unit vector directed along BO. ED vector, electric field R2 due to QD, 1 by 4 pi epsilon 0 QD by R square. We need now the unit vector along DO vector. Since unit vector along AO vector is N1 cap, so the unit vector along DO vector is minus N1 cap. Electric field R2 due to QG, 1 by 4 pi epsilon 0 QG by R square. We need unit vector along GO vector, which is obviously minus R2 cap minus N2 cap. So all the unit vectors are mentioned here. The net electric field at O is this plus this plus this plus this. If we put the value, then we observe EA vector, ED vector cancel each other. EB vector, EG vector cancel each other. So the resultant electric field at O is 0. Since electric field is 0, any charge kept here, the force on it is 0. An electrostatic field line in a vacuum is a continuous curve. That is, a field line cannot have sudden breaks in vacuum. Why not? Explain why two field lines never cross each other at any point. Since electric field lines originate from positive charge and terminate on negative charge in vacuum, there is no such charges present. So electric field line cannot originate or cannot terminate at any point in vacuum. Hence, there is no break is possible. So the electric field line is continuous curve. Then the second question says why the field lines never cross each other. If they cross each other, there will be two tangents at the point of intersection to show the direction of electric field, which is not accepted because electric field at a point has a unique direction. Two point charges QB given are located 20 cm apart in vacuum, but the electric field at the midpoint O of the line AB joining the two charges. If a negative test charge of magnitude this much is placed at this point, what is the force experienced by the test charge? So the problem is based on electric field due to a point charge, superposition principle of electric field, relation between electric field and force. This is electric field due to a point charge. This is the superposition principle of electric field. This is the relation between electric force and electric field. One charge QA is at A, QB is at B. We need the electric field at O. So electric field at O due to QA is 1 by 4 pi epsilon 0 QA by R square. The cap is from A to O. This is I cap. Similarly, the electric field at O due to QB, 1 by 4 pi epsilon 0 QB by R square. This is R. The unit vector is B to O, which is minus I cap. QA, QB value given. When we put, then we will see EB vector equal to EA vector. So the net electric field at O is E vector equal to EA vector plus EB vector. EB vector equal to EA vector, so it is coming 2 times EA vector. 2 times EA vector. Then we know all the values are converted to meter. So this is the resultant electric field at O due to the, it is actually the dipole. We need the electric force on the test charge minus 1.5 10 to minus 19 coulomb. So the force on this test charge is F vector equal to QE vector. This is Q and E vector value is this. The answer is this much. The force is this way. A system has two charges QA, QB located at the points. What is the total charge? Total charge is 0. These two charges constitute an electric dipole. Electric dipole moment we have to find. So the electric dipole moment formula you know, P vector equal to magnitude of either charge into position vector of positive charge from negative charge. So Q is here magnitude of either charge, its magnitude or its magnitude. 12 vector is at A positive charge, at B negative charge. So the dipole moment direction is from negative to positive. So that is why 12 vector is also from negative to positive. So 12 vector is this much minus I cap. Then the dipole moment formula you know, Q 12 vector, Q given, 12 vector given. After putting, the answer is along negative x-axis. The dipole moment is this way. The position vector of positive charge with respect to negative charge is also this way. An electric dipole with dipole moment is aligned at 30 degree with the direction of a uniform electric field of magnitude. Calculate the magnitude of torque acting on the dipole. The torque on the dipole is P vector cross E vector. The magnitude of the torque is P sin theta. P given, E given, theta given. After putting, the unit is coming Newton dot meter. So the answer is 10 into 10 minus 5 Newton dot meter. A polythene piece rubbed with wool is found to have a negative charge of this much. Estimate the number of electrons transferred from which body to which body. Is there a transfer of mass from wool to polythene? A polythene is becoming negative charge. So wool loses electron, polythene gains the electron. Since wool loses the electron, so wool mass reduces, polythene mass increases. Charge on the polythene piece is this much. So the electron transferred from wool to polythene is number of electron is Q by minus E, Q given minus E this much, minus E the charge of an electron. So the answer is this much. Positive mass is transferred from wool to polythene. Two insulated charged copper spheres A and B have their centers separated by distance 50 cm. What is the mutual force of electrostatic repulsion if the charge on each given? The radii of A and B are negligible compared to the distance of separation. So this says the two spheres behave as point charge. What is the force of repulsion if each sphere is charged double and the distance between them is halved. The radii and A and B are negligible compared to the distance of separation. This is Coulomb's law for point charges. Q1, Q2 given. Since that is repulsion, both charges are either positive or both charges are negative. It is written the charge on each positive. So Q1 positive charge, Q2 is also positive charge. R given. Then force 1 by 4 pi epsilon 0 Q1 Q2 mod by R square. Since Q1 positive, Q2 positive, so Q1 mod is itself, Q2 mod is itself, Q1 Q2 equal, that is why Q1 square. Then putting the value, the answer is this much. F2, this is the force when charges are double, distance halved. So the force 2Q1, 2Q2 R by 2 whole square. Here is 2, denominator, this by 2 whole square coming to numerator. So it is coming 16 times of F1. Consider a uniform electric field, the electric field along x-axis. So first question says the flux of this field through a square of 10 centimeter whose plane parallel to YZ plane. Then second question is the flux through the same square if the normal to the plane makes 60 degree with the x-axis. In the first question, since the square is parallel to YZ plane, so the normal to the square is either along I cap or along minus I cap. Then second bit says the normal to the plane, that means the area vector makes 60 degree angle with x-axis. The flux through a plane surface, if the electric field is uniform, then it is E vector dot area vector. This is applicable provided electric field is uniform and surface is a plane surface. So first question says the area vector is 10 centimeter square plus minus I cap, because the area vector can be along positive x-axis or can be along negative x-axis. Flux is E vector dot area vector, E vector given, area vector given, then the answer is, in the second case, area vector magnitude or the scalar area, E given, theta given, flux is EA cos theta. So magnitude of electric field, magnitude of area vector or the scalar area cos 60 degree. So this is the answer. What is the net flux of the electric field through a cube of side 20 centimeter oriented so that its faces are parallel to the coordinate planes? Again, the problem is based on the flux through a plane surface if the electric field is uniform. This is the cube. The faces are perpendicular to the axis or parallel to the coordinate planes. The flux through the left face, this is the left face. Electric field given, the left face area vector is this way. So the area vector is 20 centimeter whole square minus I cap. The flux is this much. The flux the right face. This is the right face. The area vector is this way. So the area vector is 20 centimeter square I cap. Electric field given. Then the flux is 120 volt dot meter. The flux through the remaining four faces, each of the remaining four faces is 0. Because electric field along x-axis, for this plane the area vector is this way. For the below plane the area vector is this way. For this front plane the area vector is towards us, and the back plane the area vector is away from us. So this surface and the lower surface and the back surface, for each the area vector is perpendicular to x-axis. So the flux through each of these planes is 0. Hence the total flux is phi 1 plus phi 2. It is also becoming 0. We can solve also this problem in another easy method. The electric flux through a closed surface in a uniform electric field is 0. So the required flux is here 0 also. Why the flux through a closed surface in a uniform electric field is 0? The flux is integration over S E vector dot ds vector. Since E vector is uniform, so E vector coming out of integration with the dot sign, then integration ds vector over S. This is 0. This is 0. So the total flux is 0. Why this is 0? Take this to be a closed surface. This area vector is now this way. This area vector is now this way. This area vector 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 this way. If we add all the area vector, so obviously the result is 0. Also another way we can verify the flux to be 0. This is uniform electric field. This is a closed surface. How many field lines enter? Same number of field lines leaving. That is why the flux through the closed surface is also 0 in the uniform electric field. So here the electric field is uniform, hence the flux must be 0. Careful measurement of the electric field at the surface of a black box indicates that the net outward flux through the surface of the box is this much. What is the net charge inside the box? If the net outward flux through the surface of the box were 0, would you conclude that there were no charges inside the box? Why or why not? It is based on, obviously, Gauss law. Flux is enclosed charge by epsilon 0. So in the first case, flux given. Then we have to find the charge. Charge is phi into epsilon 0. Epsilon 0 value and phi value. So answer is this much coulomb. Next, flux given 0. So enclosed charge is 0. Enclosed charge 0, there are two possibilities. No charge is enclosed by the box. That means inside the box you will not find any charge. Or another possibility, inside the box some positive charges present, some negative charges present, like, but the net charge is 0. A point charge is at a distance of 5 cm above a square, side given 10 cm 10 cm. What is the magnitude of flux through the square? This square can be considered as one of the 6 surfaces of a cube. So this is a cube, edge is 10 cm. The charge is at the center of the cube. The charge is at the center of the cube. So the flux through each face is Q by 6 epsilon 0. The flux through each face is Q by 6 epsilon 0. So the flux through the base also Q by 6 epsilon 0. Here the base Q, the flux through the base is Q by 6 epsilon 0. Q by 6 epsilon 0, Q given, epsilon 0 you know, then putting we find the answer. A point charge 20 microcoulomb is at the center of a cubic Gaussian surface, 9 cm on edge. What is the net flux through the surface? Gauss law says flux is enclosed charge by epsilon 0, enclosed charge given, then epsilon 0 you know. The side of the or edge length of the cube is not needed. So the flux is Q by epsilon 0. Think of this is the cube that contains the charge. If the cube expands, the flux also remains same because the enclosed charge is same. If the cube surface changes to, if the cube shape changes to a sphere, then also same charge is enclosed, the flux is also same. A point charge causes an electric flux to pass through a spherical Gaussian surface. This is the radius and the charge at the center of the Gaussian surface. If the radius of the Gaussian surface is doubled, the enclosed charge remains same, so the flux remains same. What is the value of the point charge? The flux is this much, the charge is flux into epsilon 0, epsilon 0 you know, flux this much, this is the charge. A conducting sphere of radius 10 cm has an unknown charge. If the electric field 20 cm from the center of the sphere is this and the point radially inward and points radially inward, what is the net charge on the sphere? You know, inside the conductor the electric field is 0, but here it is given the electric field is non-zero. So that is why the point must be outside the conductor. And the conductor behaves as a spherical shell of charge because the charges reside only on the outer surface. So the formula is similar to that of a point charge. If this is the conductor, spherical conductor, the charge exists only on the outer surface. This is the observation point. This is the observation point. This is r vector. R cap is this way directed. So the electric field, the r cap is this way directed. The electric field here, due to the charge behaves as if the charge is at the center. So due to q charge, here electric field is this, and the electric field is given to be this much. Pi minus, it is written radially inward. So the electric field given, we know the electric field formula, then equating we can solve q, then q coming negative of 4 into 10 to the minus 8 coulomb. A uniformly charged conducting sphere of 2.4 meter diameter has a surface charge density. Find the charge on the sphere. What is the total electric flux leaving the surface of the sphere? The flux is enclosed charge by epsilon 0. This is the surface density, means charge per unit area. The conductor area, you know, 4 pi r square. So the total charge of the conductor is q is sigma into 4 pi r square. Flux through the surface, it is q by epsilon 0. Q by epsilon 0. An infinite line charge produces electric field at a distance of 2 cm. Calculate the linear charge density. The electric field due to an infinite line charge formula is E vector equal to 1 by 2 pi epsilon 0 r lambda r cap. Lambda is the linear charge density, means charge per unit length. R is the distance of the observation point from the line charge. So this way, this is the line charge. We need the electric field here. This is r vector. This way r cap. So electric field formula is this. Here electric field given, magnitude r given. So the magnitude of electric field is lambda mod by 2 pi epsilon 0 r. So E given, R given, you know 1 by 4 pi epsilon 0. So 2 multiplied, 2 divided, so that 1 by 4 pi epsilon 0 directly value you can use. Lambda mod will found. Lambda mod knowing, the lambda is asked, which can be plus minus 10 to minus 7 coulomb per meter. Two large thin metal plates are parallel and close to each other. On their inner surfaces, the plates have surface charge densities of opposite signs and magnitude given. What is the electric field in the outer region? Also, the other outer region between the plates. The electric field due to thin plane infinite sheet of charge is E vector is eta by 2 epsilon 0 n cap. Eta is the surface density of charge. On the first surface, charge exists. On the inner surface, no charge. On the outer surface, on the second sheet, charge exists. On the inner surface, no charge on the outer surface. So for the first sheet, the surface density of charge is equal to the sigma 1. For the second surface, the surface density of charge is sigma 2. Sigma 1 given, sigma 2 given. Eta 2 equal to sigma 2, eta 1 equal to sigma 1. So eta 2 is equal to minus of eta 1. Electric field RT due to this sheet is eta 1 by 2 epsilon 0 minus I cap. Electric field RT due to this sheet is eta 2 by 2 epsilon 0 minus I cap. So the total electric field RT due to the two sheets is eta 1 by 2 epsilon 0 minus I cap plus eta 2 by 2 epsilon 0 minus I cap, it is coming 0. Electric field here due to this sheet is eta 2 by 2 epsilon 0 I cap due to this sheet eta 1 by 2 epsilon 0 I cap. So the total electric field here is coming 0. The electric field here due to this sheet is eta 1 by 2 epsilon 0 I cap due to this sheet is eta 2 by 2 epsilon 0 minus I cap. So the total electric field here is this much. It is equal to eta 1 by epsilon 0 I cap. Then putting the value, we got this much. Electric field 0, electric field 0. Here electric field this much, directed this way. If 10 to the power 9 electrons move out of a body to another body every second, how much time is required to get a total charge of 1 coulomb? 10 to the power 9 electron moving in 1 second. So the required time is 1 coulomb by 10 to the power 9 into electron charge. Actually this much coulomb in 1 second. Charge is transferred. Total 1 coulomb we need, so that is why T is coming 1 coulomb by this much. Coulomb's law for electrostatic force between 2 point charges, Newton's law of gravitational force between 2 point masses, both have inverse square dependence, means both proportional to 1 by r square. Compare the strength of these forces determining the ratio of their magnitudes for an electron and a proton and for two protons. This is electrostatic force between 2 point charges, magnitude. This is magnitude of gravitational force between the 2 point masses. First question says between electron and proton. The numerator is magnitude of electrostatic force between electron proton. Electron charge, proton charge, both are same. Each is E magnitude. Then the gravitational force magnitude is m is mass of the electron, mp is mass of the proton. R square same, cancelling. K, you know, 9 into 10 to the power 9. E, you know. G value also you know. MEMP you can put, then the result is 0.3 10 to the power 40. Ratio of magnitude of electrostatic force to the gravitational force between two protons. Same way, here is MP, again also MP. Estimate the acceleration of electron and proton due to electrical force of their mutual attraction when they are 1 angstrom apart. Proton mass given, electron mass given. This is the magnitude of electrostatic force between 2 point charges, and Newton's second law says force is equal to mass into acceleration. So magnitude of electrostatic force between proton and electron, proton charge, electron charge magnitude same, each is E. Then this is the magnitude of electrostatic force between proton and electron. AE, AP, magnitude of acceleration of electron and proton. Since the electrostatic force obey Newton's third law, force on electron magnitude equal to force on proton in magnitude. So force is mass into acceleration magnitude. Again the force is mass into acceleration magnitude. So acceleration of electron magnitude, acceleration of proton magnitude. A charged metallic sphere is suspended by a nylon thread. Another charged metallic sphere B held by an insulating handle is brought close to A such that the distance between the centers is 10 cm. The resulting repulsion of A is noted. This is A sphere. This is B sphere. We consider both spheres to be point charges. This distance given 10 cm. A charge let Q1, B charge let Q2. Since they repel, the charges are like charges. Sphere A and B are touched by uncharged sphere C and D respectively. C and D are then removed. This is sphere C. It will touch to A. This is sphere D. It will touch to B. C will touch to A. D will touch to B. C touching to A. Now A charge shared between A and C. So A charge becomes Q1 by 2. C charge also becomes Q1 by 2. D sphere touches to B. B charge is shared between B and D equally. So B charge becomes Q2 by 2. D charge becomes Q2 by 2. The charge sharing occur to equalize the potential of A and C and to equalize the potential of B and D. Since A radius, C radius same, A potential, C potential same, so A charge, C charge same. B radius, D radius same, B potential, D potential same, so B charge, D charge also same. C and D are then removed. B is brought closer to A. The distance become 5 cm between their centers. So in the second situation, A charge becomes Q1 by 2, B charge becomes Q2 by 2, and the separation becomes 5 cm. This is the magnitude of electrostatic force. You see the potential of two spheres same. If radii is same, charge has to be same. Let Q1, Q2 are the initial magnitudes of charges on A and B. Finally, A charge becomes Q1 by 2, B charge becomes Q2 by 2. The initial separation was 10 cm. The final separation is 5 cm. So the initial force magnitude is 1 by 4 pi epsilon 0 Q1 Q2 mod by R1 square. R1 is 10 cm. The final force magnitude is 1 by 4 pi epsilon 0 Q1 by 2 Q2 by 2 5 cm whole square. So F final is equal to F initial. Consider three charges Q1, Q2, Q3 each equal to Q are the vertices of an equilateral triangle of side L. What is the force on a charge Q placed at the centroid? The electric field due to point charge. The relation between force on a test charge and the electric field. So electric field R2 due to Q1 charge. Electric field R2 due to Q2 charge. Electric field R2 due to Q3 charge. R1 cap unit vector along AO vector. R2 cap unit vector along BO vector. R3 cap unit vector along CO vector. Clearly E1 equal to E2 equal to E3 because it is given Q1 equal to Q2 equal to Q3. The resultant electric field at O, E1 vector plus E2 vector plus E3 vector. E1 vector, E2 vector. The angle between them is 120 degree. E1 vector plus E2 vector is E1 square plus E2 square plus 2 E1 E2 cos 120 degree minus R3 cap. E3 vector, you know E1, E2, E3 magnitude same. So this becomes E3 square 2 E3 cos 120 minus R3 cap E3 vector. Cos 120 minus half. So this is becoming minus E3 vector. So the resultant electric field at O is 0. Since the electric field at O is 0, any charge kept at O, the force on it is also 0. Because electric field is 0. We can solve this problem by another method. E1, E2, E3 same. And this angle is 120 each. So by Lami's theorem, E1 vector plus E2 vector plus E3 vector has to be 0. Consider the charges Q, Q, minus Q, minus Q, Q, Q. What is the force on each charge? Again, the problem is based on electric field due to point charge and the relation between electric field and force on a test charge. The force on Q by Q is this. R cap AB unit vector this way directed. The force on Q by this is this much. R cap AC unit vector directed this way. Let us assume Q is greater than 0. So this is positive. The force is along r cap. This is negative. The force is opposite to r cap. So F vector AB is this way. F vector AC is this way. Magnitude of the two forces are same. This is a rhombus. This is 60 degree. This is 120 degree. So this is 60. This is also 60. The resultant magnitude is a square plus b square plus 2ab cos 120. The electric force on minus q by q. R cap CA unit vector this way. Since it is negative, the force is opposite to r cap. So the force is now this way. The force on minus q by q is this. R cap CB unit vector this way. The force is negative, so the force is this way. This force magnitude same. It is a rhombus. This is 60 degree. This is 30. So the resultant force is now this way. Its magnitude is a square plus b square plus 2ab cos 60. The force on q by q is this. R cap AB unit vector this way. The force is also this way because it is positive. The force is this way. The force on q by minus q is this. R cap BC is this way. Minus R cap BC. So force is opposite to R cap BC. The force is this way. This force magnitude same. It is a rhombus. So it is 60 degree. It is 60 degree. The resultant force magnitude a square plus b square plus 2ab cos 120 degree. An electron falls through a distance of 1.5 centimeter in a uniform electric field of magnitude. The direction of field is reversed, keeping its magnitude unchanged, and a proton falls through the same distance. Compute the time of fall in each case. Contrast the situation with that of free fall under gravity. Force is test charge into electric field. Force is mass into acceleration. Here the acceleration is uniform, so we can apply S is equal to ut plus half d square. In this case, electric field downward. Electron, the force is upward, then the electron will go in this direction. Force magnitude is EE. Acceleration magnitude. When it is proton, also same force, because E is proton charge or E is also magnitude of electron charge. In both the problems, electric field magnitude is same. So acceleration of electron find by this way. It is the magnitude of acceleration of electron. It is magnitude of acceleration of proton. It is mass of electron, mass of proton. So the acceleration of electron is more because the mass is less. Acceleration of proton is less because the mass is more. In both the cases, initial velocity is 0. So s is equal to half at square. This is for electron. Then the time is asked. So time is found. And when it is proton, electric field this way. Proton, so electric field, since this way, proton will move also the same way, means in the upward direction. In the same way, the time for the proton is 2s by ap, that's root over. 2 point charges given, placed 10 cm apart. Calculate the electric field at the points A, B, D. This is one charge. This is the next charge. We have to find electric field here, here, and here. This is the end-on point or the point on the axial line. This is the broadside point. That is the point on the equatorial line. This point also can be considered as point on the equatorial line with r equal to 0. So for A, we can solve in two ways. In one way, electric field here due to Q1, electric field here due to Q2 are then. So this is based on this formula, total field. At B, electric field due to end-on situation. At D, electric field in broadside situation. At A also, we can apply this formula by replacing R to be 0. The electric field at A due to Q1, the electric field at A due to Q2 are same. That is why the net electric field at A is 2 times of this. Q1 is positive charge, Q2 is negative charge. So the dipole moment is this way. This is the dipole moment. The electric field at B is this. The electric field at D is this. The electric field at A also we can find by putting this to be 0. So this answer will match with this. Two charges plus minus 10 microcoulomb are placed 5 mm apart. Determine the electric field at a point D on the axis of the dipole 15 cm away from its center O on the side of the positive charge as shown in figure. This is 10 microcoulomb. This is minus 10 microcoulomb. This is the center between the two charges. We have to find the electric field at D. This is the point on the axial line, or we can call this the end-on point. The distance is 15 cm. It is very much greater than the separation between the two charges. So we can treat the dipole to be as ideal dipole. So for the ideal dipole at the end-on point, the electric field formula, the dipole moment directed from negative to positive, r 15 cm. Then the electric field is now also directed along positive x-axis. Two charges plus minus 10 microcoulomb are placed 5 mm apart. Determine the electric field at the point D. So this is the dipole. This point is the point on the equatorial line, or it is the broadside on point. Again, the distance is much greater than the separation between the two charges, so the dipole behaves as an ideal electric dipole. Hence the formula for electric field is this. The dipole moment R is OD given, then the electric field we can solve. The electric field is opposite to positive x-axis. That means the electric field at D is this way. The electric field components in figure 1, Ex non-zero, Ey, Ez 0. So the electric field is along positive x-axis. Alpha given, this alpha when we need we can put here. Then flux through the cube is asked, and the charge through the cube also we have to solve. A given 0.1 meter, this is 0.1 meter, this is also 0.1 meter. The flux through a plane surface in the uniform field and Gauss law says Q by epsilon 0 is the flux. Electric field is EXI cap. The flux through the left face. Electric field here dot the left area vector. The left area vector is this way directed. The flux through the right face is here electric field dot the right area vector. The right area vector is this way directed. The flux through each of the remaining four faces is 0. So the total flux is this plus this. Total flux is enclosed charge by epsilon 0. Then we can find the enclosed charge. An electric field is uniform in this side and has this value. The electric field is uniform this side and has the value. What is the net flux through each flat face? It is a flat face. It is a flat face. What is the flux through the curved side? What is the net flux through the cylinder? What is the net charge inside the cylinder? Again the flux through a plane surface in the uniform field. For finding the charge, we will apply Gauss law, flux equal to Q by epsilon 0. The flux through this face is here electric field dot this area vector. The flux through this face is here electric field dot this area vector. The flux through this curved side, it is 0 because electric field is perpendicular to area vector. The net flux is, we have to add this flux with this flux. Obviously this flux is 0, so the net flux is this plus this. Net flux knowing, then the enclosed charge we can solve. An early model for an atom considered it to have a positively charged point nucleus of charge Zd surrounded by uniform density of negative charge up to a radius capital R. The atom as a whole is neutral. For this model, what is the electric field at a distance of R from the nucleus? Here the problem is based on Gauss law, and the flux is enclosed charge by epsilon 0, and the flux is surface integral of electric field. For this P1 point, this is R1 vector, the flux is enclosed charge by epsilon 0, the flux is E vector dot area vector. So it is coming E radial component into 4 pi r square. The flux is enclosed charge by epsilon 0. Enclosed charge is the nucleus charge plus this much negative charge. Rho is charge per unit volume. Rho is negative charge per unit volume. Actually, the negative charge minus JD occupies this region. Its volume is 4 by 3 pi r cube. So rho is the volume density of negative charge in this region. We need this much negative charge. So this much negative charge is rho into this much volume. So rho into 4 by 3 pi r cube. Then the flux is this much, also this by epsilon 0. Then we can solve E1. And E1 vector is multiplied with R1 cap. This formula is applicable for R1 0 to R. Now we need the electric field at P2. So similarly, the flux is E into 4 pi r square. Then this should be enclosed charge by epsilon 0. What is the enclosed charge? This is the totally enclosed charge. This is JD and this is minus JD. So the enclosed charge is 0. That is why E radial component is also 0 and electric field is also 0 at P2.